Hi everyone, thanks for attending my talk. Today I'm going to talk a little bit about the exciting work we do at EDF R&D regarding computer vision and remote inspections. So we're going to start with, okay. We're just going to give a little bit of a context of what we do. Then I'm going to talk about a particular case study where we have used computer vision for remote inspections for the case of wind turbines. And then I'm going to conclude with some overall perspectives. So as you are aware, EDF is a major player in the energy sector in the UK. The whole nuclear fleet of the UK is operated by EDF. In addition to that, there are 37 wind farms, 2 of them offshore. And the investment in offshore is going to continue increasing in the next years. There is still one gas-powered station which was set to stop this year, but actually it was extended for the winter to help with the ongoing energy crisis. And 2 EPR reactors in progress at Hinkley Point. So the numbers I'm showing here are already a few years out of date. Apologies for that. But basically, wind is going to become a major part of EDF's renewable strategy in the UK. So as we move away from nuclear power, because a lot of the nuclear power plants are now entering a phase of decommissioning, so they are going to stop eventually, the plan is to invest more in other forms of energy, renewable energies. So given this, it is very important then that we are able to know what is going on with our energy assets. This is why inspecting and monitoring is so important. For example, for solar panels, have to be aware, these panels are exposed to the conditions of the weather. Things could happen like cracking and corrosion of these panels that might affect performance. For nuclear as well, the graphite bricks that are used to regulate the reactions can also suffer cracking and deform over time. It is important that we have to monitor them constantly for the safe operation of the nuclear power plants. And of course, on wind energy, wind turbines. Wind turbines, once again, can be exposed to very harsh weather, a lot of difficult conditions. So it is important to be able to inspect these turbines regularly, understand what kind of damages or deterioration they are facing, to be able to do the appropriate maintenance and to ensure the safe capability of generating green energy. So this is the topic that I'm going to focus on today, wind turbines. So just to maybe emphasize a little bit more, wind energy is going to play a major role in the future for generating green electricity. There are currently 13.8 gigawatts already of capability already installed worldwide, and there are 60 gigawatts in projects in development. In the UK, as I mentioned, there are 37 wind farms, 2 of them onshore. The new trend is that offshore wind, and especially floating wind, is going to be very valuable in the future because that allows us to put wind turbines on environments that have where we can extract more energy from. Especially the situation in the UK is very favorable because the seas around the UK are shallow, and as you know, the UK is windy. So UK is a key asset for wind energy. And of course, we're aware that governments are also aware of this. As part of the British energy security strategy, there is a target of having 50 gigawatts of offshore wind in the UK by 2030, and a similar target was set in France for 40 gigawatts. So this is just once again to emphasize that wind is a major player. But then we have to understand as well what can go wrong with wind turbines. So, of course, wind turbines are exposed to a lot of erosion, weather, lightning, and different type of damages may appear in these structures. There could be some cracking, there could be some erosion, other kind of things. So we need to be aware of this. And how do you become aware of this? Well, in the past, It used to be that you would set someone all the way up there to inspect them. However, that is really dangerous. Nowadays, what is done is remote inspections. So either you can use drones to take photographs of the images through some scheduled flight path, or you can also do ground-based photography, where you rotate the wind turbines to capture the different angles of the blades. So what is, however, this is still a little bit of a difficult task, because what happens after you come back from these remote inspections is that you come back with thousands and thousands of high-resolution photographs, and then a blade engineer, a highly skilled expert, has to sit down and look at these high-resolution thousands of photographs for a long time. It takes approximately 4 hours to inspect the photographs of the 3 blades of a single wind turbine. So, of course, this is not the best use of their time. So what we wanted to do was to help them reduce the time they have to invest in this by building a computer vision solution that can automatically scan all of these images and identify different type of defects that may be appearing in the blades, show you where they are and what type of defects they are. So this is the main solution that I want to talk about today. So how do you embark on building such a solution? Of course, the development of this project has been has had a long history, but basically just to summarize it for you, how do we usually start this type of projects? Well, first, you have to start by identifying the opportunity, talking with the domain experts, understanding the pain points, having interviews, and basically putting yourself in their shoes to understand exactly what kind of situation they are facing. Afterwards, we usually try to get some initial data, whatever data we can get our hands on, just to get started with, to try to understand, to assess the feasibility of solving this task and up to what extent we can help. Afterwards, minimum viable product. This is where you say, okay, well, with the little data that I have in hand and with this limited time that I have at the moment, I was able to build this. And based on that, you can evaluate, okay, maybe this could be useful, this could lead to something interesting. In other cases, maybe it will be, okay, actually, maybe nothing can come out from this. But this is usually the line of how we start and how we decide if we want to carry on with carry forward with a project or not. Afterwards, of course, there's the iterative development of the project, and we are currently nearing the final stage of development right now. We are very close to handing over a solution, putting this solution in the hands of the engineers so they can start now testing it, giving us feedback, and finally start using it in operation. We will conclude that this year, and afterwards, of course, you have to enter a phase of regular monitoring just to make sure that the solution that you have built will continue working through time as conditions changes. Maybe tomorrow you will have a different inspection providers, maybe they will do something different about the drones or the photographies or whatever, so you gotta make sure that the solution that you're building today will continue working later on. So I want to show you very briefly a little bit about the data that we're working with. We're mainly working with data from 2 inspection providers. One of them is SkySpecs that do drone inspections, mostly for North American sites. And these are the type of images that you can get, that you will get back from them. So the drone flies around the turbine, takes photographs, and as you can see, you can get a wide diversity of backgrounds in the images, which poses a further challenge. The other one is Cornice, which is ground-based photography, and this is mainly for wind sites in France and in some other countries in Europe. So in this case, the pictures may look a little bit more cleaner because the background is always going to be a sky, but in some cases you may still have things like clouds. Maybe in rainy days the photographs will not look that bright, these kind of things. And the bar chart, where you can barely see the labels, just indicate the different type of defects that may be identifiable in these images. And the top ones, the top 2 are cracks and erosion. Cracks occur when the different, I guess the name also already explaining it. It's basically a crack that is occurring on the surface of your wind turbine, and if you don't address it, then it can grow, and it can lead to a further bigger damage, up to the point where maybe you will have to stop the operation of wind turbine. Similarly, erosion occurs mostly due to the wind, and rain as well. These are the two main defects that the blade engineers are concerned with, that they approached us and told us, okay, these are the main things that we want to be able to automatically detect. Everything else, maybe you can put it in a different category as others, but we need to be certain that we can identify this type of defects. So, however, it's not always an easy task. And in the previous panel, we just talked about the value of getting better quality data. And this is a situation that we also faced in here, because even though we had high resolution images that were already annotated by engineers, not all of the annotations were really useful for what we're trying to build. And this is basically because when the blade engineers annotate some defects, they didn't really have in mind that this would be it would be used for building a machine learning model. Just to explain that a little bit better, we are using historical data from inspections of previous years, even before the conception of this project. So this label data was already what the engineers were doing in their normal day-to-day operation. And in this case, you have to do some data cleaning to identify the cases where that may be useful for you, that you want to keep, and some other cases that you do not want to keep. And this can be a little bit challenging sometimes with images, because whether if you have tabular data, maybe you could do some histograms, do some statistical checks, you can plot some things, you can draw some statistical measures. If you're starting from images, it's a little bit more complicated, because unless you do some feature extraction from the start, then how do you do this type of statistical analysis? So we have to come up with some solution to try to identify these cases that we wanted to get rid of, the cases where we would have on the image a large portion occupied by the blade, but also a large annotation. And this can occur when a lot of very small cracks appear close together all throughout the blade, and the engineer just labeled it as a single one. So once we identified these general type of cases, what we had to do was to gather the whole team and then sit down for 1 week to do a re-annotation of those type of images that were hurting the performance of the model. This was once again, of course, with input from the domain experts, from the blade engineers. And this is something that it is really important to highlight. You must at all times have inputs from the domain experts. They are not only will they be the users, the people that will be using your model, but also they are the experts in the field. And you have to take into account their knowledge and their understanding to be able to actually solve the tasks that you want to solve appropriately. So here I'm showing some examples of the original annotations, for example, that were not very precise in some cases, and the proposed annotations that we had to do. And based on that, we could then start training a model that could hopefully detect these defects. But before that, we took an additional step of doing some background subtraction. And the main reason for that is that in early iterations, doing some error analysis and a little bit of explainability on the model of the early models, we noticed that there were in some cases a lot of confusion due to the backgrounds in the images. As I showed before, you can have very different backgrounds, and sometimes some of these models may mistake things that are occurring in the background for actual defects. So in order to reduce this type of noise, we also did some background removal using a model called Tracer. It's really interesting. It's basically a salient object detection with guided attention. It was presented, I think, just last year. And we obtained really good results for this type of background subtraction. So Afterwards, we can now move to defect identification. And here I just want to show a few examples of exactly what type of defects we are looking at, we may encounter. So in some cases, well, we can have cracks, which are indicated in red. And in some cases, this may be very evident, large, black, long lines that occur on the blades. But in some cases, it may be much more subtle, like the small red annotation that is on the top right. So in that case, there was a lightning strike on the yellow part, and when there is a lightning strike, due to the difference in temperatures that it leads to in the material, some additional cracks may form around the area of the lightning strike. And this is something that as a data scientist or a machine learning engineer, you don't just casually know, right? This is where the input from the domain experts really comes into place, because otherwise we would never be able to identify, to have the type of detail for this type of situations. I already mentioned the others, which could be, for example, lightning strikes or any other type of damages, and erosions, mostly due to the wind, or to icing, or in general due to the weather, are also indicated in cyan in here. And when trying to approach this model, when trying to approach this task, we also had to ask ourselves, okay, how are we going to frame this question? And if we want to improve the annotations, what type of annotations we should be using. So normally, maybe you would think about using object detection, because you already know the type of things that you are looking for. However, there are a few challenges for doing that in this case. And one of the main challenges is that in some cases, the object that you're trying to identify may only occupy a very small part of the image and may occur at some odd angle, which is the case that I'm showing in here. So in this picture, we're looking at the leading edge of a blade with some snow on the background. So you can already see that just identifying the blade in here is already challenging because it's the same color as the background. And then what we see here, the black line along the edge indicates the zone of erosion that we want to identify. And if you were to just put a bounding box around it, you would end up with the proposed cyan box in here, in which approximately 5% of the box is the object you want to identify, and everything else is background. And this is precisely the situation that we're trying to avoid. Even if you impose the background subtraction method that I explained before in here, it may not always work so well for defects that occur at weird angles inside of the blade. So instead of that, we opted for an instant segmentation approach. And this is reflected already in the type of annotations that I'm showing in here, where you can have polygons outlining the contour of the defect. So putting both of these things together, and after a lot of work, we are now in a position where we have a model that is able to identify and highlight the different type of defects occurring in the blades, giving you the exact, not the exact, but the approximated outlines of each instance. In some cases, if different things are occurring very close together, such as the fatigue cracks that are shown in the picture in the middle, okay, you may end up with this type of rectangular things, but this is only up to some tolerance. If there are objects that are sufficiently far apart or different, then they will be tagged differently. So we go from a picture where maybe the original annotation was just a single big rectangle for the whole image, where now we can tell you exactly, okay, the fatigue cracks that you're looking for are exactly here, 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 and so on. And each different type of defect is indicated with different colors, such as the case on the right there. So this is something that the engineers can use to filter by defect, to look for different things. And one of the things that they really appreciated about this approach is that compared to the current solution that they have at the moment, where the inspection providers do some basic analysis trying to identify the errors approximately, our approach can highlight the approximated shape of the defect. So in here, you have a tricky case where you have a crack that is doing like a half circle shape. So before, this would be indicated by just maybe like one big rectangle. In the best case, maybe a rotated rectangle. But in here, we're able to give you exactly the outline. So yeah, so this is a really interesting tool, has been a really interesting project, and it's a very clear example where computer vision is going to provide a lot of value for this type of remote monitoring of energy assets. With this type of solutions, we can now immediately discard those images that definitely do not contain any damage, so they do not need to be inspected. For those where some damage is detected, the engineers can then choose to focus, okay, which images they want to look at. For all the predictions, the model also outputs a number that can be interpreted as a level of confidence, and then they can choose to filter out, okay, I want to look at maybe this prediction is only like, I don't know, 60% confidence, things like that. Okay, then you can focus on this type of things. So yeah, this is going to greatly help the engineers and reduce the time that they have to spend looking at this type of defects. And it is important to understand, of course, that what we're doing here is not replacing the engineers. We will never be able to do that because we will never realistically get a model that can get 100%, that can be 100% right all the time. But we're building a tool that the engineers can use to make their work easier. So yeah, maybe I just want to finish with some perspectives, and then we can have some time for questions. What happens after this? Well, another interesting question that you may ask is, okay, you are now able to tell me where the damages are. Can you now tell me how this is going to evolve? How is this going to look how is this going to look like in the future? Based on that, maybe you can choose to choose to take action, or if you want to leave it like that. So I don't know. For example, one interesting idea that I had is like, okay, how can we connect this with a digital twin of the blades, right? So if we have images where we can automatically identify the defects, we can then pass these defects to the digital twin, and then we can do the physical modeling to understand the evolution of the defect, and then based on that provide additional value. And outside of wind, of course, there are many other use cases for remote monitoring, computer vision or remote monitoring. As I mentioned in the start, of course, PV panels is another interesting option where you can remotely assess the state of your solar farms. Coastal erosion, as we know, climate change can impact the water levels and vegetation around coastal areas. And it just so happens that most nuclear assets are in coastal areas. They need to be for the water intake cooling systems. So how is climate change going to impact the safety and the structure of nuclear assets? This is something that we also need to be able to understand. And in general, also site condition monitoring. So as I mentioned before, a lot of the nuclear power plants are now entering a phase of decommissioning where you are uninstalling a lot of equipment, moving things around, a lot of people and construction equipment going in and out. So how can you make sure that your structures, your facilities are still safe for people to operate in them? So yeah, maybe these are just some ideas that I thought about that could also be interesting. And that's it.
Are there any questions?
Hi, Gustavo. It's a very good presentation. I have a question about your next step, deployment. I take it it's not yet deployed, but do you have an idea how often will they make those inspections? And did you consider any alternatives to creating a digital twin to predict the results of the damage? Thank you.
Right, so about inspections, I believe that remote inspections are carried out approximately every 6 months, depending on the site and the conditions. And it is after these inspections that you get these thousands of pictures in return. So the solution is not something that needs to be live 24/7, that the engineer needs to put an image at any time of the day and get an immediate response. No, this is something more that will be used a few times during the year. And then based on that, you can probably think that maybe this volume of images will be submitted as a batch, and then the model can perform inference somewhere on the cloud, and then after a while return and display the results in an interface that we can build for the engineers, where they can visualize the images and also obtain a report of their results. And for the digital twins, yeah, as I mentioned, that's also an area that I'm interested in. I cannot yet answer clearly what the next step for that will be. I am aware that there are other companies that are already doing digital twins of wind blades. So it's not something that necessarily we have to do from the start, or that we have to build ourselves from the ground. But that's something that I cannot really, I don't really know yet. That's up for planning.
Okay, first, thank you for the presentation. I have a question about the detection. You say that you have like a way to ignore some detection because they are bigger, like they are big. What about the distance? Because if the drone is close to the object, it's gonna be bigger, and it depends on the position of the drone. How do you deal with that?
Right, so for the drone images, these are accompanied by some metadata that we can look at, understanding, for example, the angle of a drone, and then more or less the equivalent of how much a pixel is approximately in terms of the real measurements, like centimeters, in that image. And also the flight path of the drone is already pre-programmed, is already standard. So all of these things are already taken into account, such that if you have a set of continuous images of the blade, they will all have been taken at the same distance, not at different distances. And yeah, it is true that maybe there could be some defects that are just naturally large. They actually occupy a large area. However, that is not really the case for the two main type of things we want to try to detect: cracks, which are usually thin, long lines, and erosion, which are also extended lines, not so thin, but can also be extended lines. There may be other type of defects that could occur. And it is true that by not accounting for that, there is some noise in the data, but that's also where this other aspect of looking at the confidence level of the prediction comes into place.
Hi. I was glad to see the good results with Tracer, and I'm wondering if you tried taking the results from that that worked, that you got nice segmentations from, and imposing a more challenging background in order to augment your training set, in order to then potentially do better on hard background scenarios. So yeah, did you try that approach, or do you think that might be an interesting one?
Well, to be honest, I think some of the backgrounds we already have are already kind of challenging, such as this one, for example, the one with the snowy fields. I mean, unless you actually zoom into the photograph, it's kind of hard to tell when the blade starts and finishes. Other type of backgrounds, such as the one shown in here, where you may have different things on each side of the blade. Maybe on the lower right, you will have some dirt, and then on the upper left, you will have some grassy field, these kind of things. So we didn't pursue testing on more challenging backgrounds. Yeah, because we consider the level of the challenge was already good enough.
Cool. Thanks a lot.